app, you have one per user or per thing. And basically the bottom line is instead of going with a constant number of data stores, you have a number of data stores or a number of units of computation that are pretty much linearly related to how much work you're trying to do. Now the issue with that is that sharding is a first world problem. People don't shard unless they have to. People don't shard unless they're the size of Facebook, and basically it's the only option left. It's because anything else would break. So why would you want to do that deliberately? Well, first of all, it's important to remember that there's a huge difference between doing something because you absolutely have to and it's your last option, and doing something because you've probably prepared for it and it's in your design from day one. And it turns out, as with many things, that restrictions can foster creativity, and actually that restrictions can become a strength. For example, it turns out that this kind of design has very, very interesting performance properties. And I've already made the argument that it's actually born from trying to scale something up, but it actually also scales down very nicely, somewhat dependent on which tools you use. It also has obvious economical advantages. First of all, most cloud providers' offerings are very scalable, especially EC2 or Amazon Web Services is a perfect example of this. You pay as you go. Now, if it's very easy, and then I don't just mean that it's possible, but it's also very easy to scale up and down on even short time frames, then you don't have to over-dimension how many machines you have, how much resources you have, so you end up paying less. So obviously, and there's also other reasons why, for example, long-term storage, why this ends up being significantly cheaper than the more traditional setup. Now, I'm not proposing this as a silver bullet. This absolutely does not, by any means, magically remove all of the previous things, all of the previous work that has been done. It does not, and it's certainly not a solution for absolutely everything. But for some things, it can be the right tool for the right job. So, and the kind of job that it's typically well suited to is one where sort of every single user primarily interacts with their own data. So as long as, well, obviously, as long as there's one obvious sharding vector, so that you can just say, well, every user gets their own data store, and as long as users don't really need to access other people's data stores very often, then sure, that'll work out. So if people are basically interacting with everyone else at any given time, then it's probably a very bad idea. Now, one example of something where I think it would work out great is if you're trying to make webmail or some new email app or email service. Now, at first sight, that might seem contradictory because email is the definition of an application where everybody's talking to everyone else. Now, that's true, but the interactions between different people are pretty much just SMTP. You fire that off somewhere, and it doesn't really matter very much. But most of the interactions that people are doing are actually with their own data. They're reading email, they're sending email, which is essentially just internally moving things from an out box to a sent box, and then maybe doing some SMTP on the side. They're tagging things or querying by tag, or either way, they're primarily working on their own data. And in fact, the ability to do that with other people's data would be considered a security problem. So if you applied this to the idea of a completely fractal architecture, and you really take the idea completely to the extreme, then that would mean that you have the GUI database and cachey thing at the center, you have an application layer on the outside, and then you have this SMTP servicey thing on the edge. Now, you could also say, well, let's just have the fractal thing that I described before and consider SMTP to be some external service the way that you would have traditionally considered it an external service, or that you would consider so many things an external service. For example, if you're on Heroku, then even your database is an external service. So let's ask Python for advice. If you don't know what this does, there's been so many Zen of Python talks, I can't imagine that there's that many people that still that have not come across this, but essentially just type this into an interpreter and you will get a bunch of nice koans or a bunch of nice aphorisms about Python. One of the things that import this says is that special cases aren't special enough to break the rules. So if you take that literally in this case, then you would have to say, well, you can't just say that SMTP is special and it has this own service that's spread off, that's separated off, but everything else is in one unit of computation. Well, is in 1 unit of throughput. But on the other hand, practicality beats purity. And I think in this case, it actually significantly wins out because it's a very bad idea to design your email application in a way that's completely indistinguishable from it being a spam botnet. And the other reason is that if you are a startup, so when I made these slides, Sparrow was not yet bought out by the Gmail team. If you have a startup that is trying to completely revolutionize email, then the way that you're going to try and win is by having a fantastic UI. I mean, email, from the point of view of the user, is pretty much binary. I mean, you either succeed in delivering messages and receiving messages, or you don't. And if you don't, then, I mean, you've already lost. So it doesn't matter how good your UI is. So in the beginning, it might make perfect sense to actually, even if you're a complete web shop, to get the actual delivery of email and the receiving of email, get that done by a completely different company that's already specialized in that. For example, Mailgun. There's another thing that I think it might be a very good idea for, that is Diablo 3. Now, I've had to cut these slides a little bit to fit into this time slot so that I would still have time for questions. If I end up with enough time at the end and people are interested in it, then I'm more than willing to give that part. But basically, Diablo 3 is another example of where I think it would work. So what sort of tools can you use to build an application with a fractal architecture? Well, the important part, obviously, is persistence, since the thing that clearly doesn't fit in this very distributed, very separated off model is the traditional centralized database, such as Postgres. Now, I use SQLite. SQLite is the obvious choice here simply because, well, if you want tons of small databases, well, SQLite, it doesn't get any simpler than SQLite. And it runs pretty much everywhere. It's very fast. It's very well supported. It comes in the Python standard library, so there's not much more you can ask for. Now, on top of SQLite, I use an object database called Axiom. Now, who in the audience knows who or what Axiom is? 2 people. Okay, because I told Mache, and this is the first. I think this is one of the few audiences in the world where someone would actually know what Axiom is, because it is somewhat obscure. But in order to try and plug it, first of all, why do I like Axiom? Because it's incredibly simple. So it's sort of ORM-y. It's more of an object database than an ORM. But one of the things is, for example, that there's one-to-one mapping between tables and objects. If you want to join table, then you're going to have a join object. That might sound like a lack of feature, but really, the Axiom itself fits in your head. And honestly, when you're doing, when you have an abstraction over join tables from your ORM, it's not like you can forget that underneath there's actually secretly a join table somewhere. You still have to understand how relational databases work. It's built on top of SQLite and only SQLite, which again might sound like a limitation, but actually makes many things significantly simpler. And also many of the things that Axiom does simply wouldn't be possible for it to do them if it had to support every single database out there. You can use it in memory, so basically you can just use an in-memory SQLite store, or you can even use it without a store at all. So it's very, very easy to just open up a REPL and start playing with Axiom. Like I do this regularly, and basically just play with it and see what it does. But at the same time, despite being simple, Axiom is also incredibly sophisticated. For one, it comes with a schema upgrade system that actually works. So basically what happens is you have objects in a database, and you can upgrade them to newer versions and from any previous version, and it will basically just figure out how to get you to the newest version, and it will live update data without having to run migrations or anything like that. And you can add new things to a model, you can remove things from a model, you can even add new objects during the upgrade if you decide that there should be some more composition in your data model. And in fact, what you can actually do in an upgrade is kill the previous object and create these and new ones. So essentially, I've never come across anything that anyone has wanted to express in terms of objects or tables that an Axiom upgrader couldn't somehow figure out how to do. And all of this actually works. It's honestly the nicest schema upgrader that I've ever seen. It also is very, very strongly typed. So for example, for Python 3 forward compatibility, you do not get to play fast and loose with bytes and Unicode in Axiom. It will complain. It comes with nice features such as a scheduler. So you can basically have persistent things, and you can just say, well, I want to run this at some point, like I want to run it on January 1st, 2014, and it will remember that, and assuming that obviously the process is running on January 1st, 2014, it will run it whenever it needs to. I've used this to implement the feature that most people would use queues and workers for. So basically asynchronous tasks that end up being done at some point in the future. It's obviously not entirely the same thing as a worker queue, but you can implement very similar things with it. I have not yet tested it in the face of YouTube's famous stampeding herds problem. So essentially, the stampeding herds problem is that if you have a distributed system, then eventually many of your tasks will end up happening at the same time, or at least they won't be evenly distributed. So even though you think you have some like 20% over provisioning of your resources, but then it turns out that all of these things add up, and you have this perfect storm that like completely takes down your cluster. So fortunately, the way YouTube has fixed this is adding a lot of jitter on when things get executed, or basically accepting jitter everywhere. And it's really, if you're already using a time-based scheduler, then obviously it's very easy to add more jitter. So I think it will do fine, but I haven't run into this problem yet. It also comes with file storage. So anyone who's ever had to deal with some wonky MySQL database somewhere that thinks that it's a file system, and then had to deal with interesting things like file encodings, this comes with actual, real, honest-to-God file storage. And it has a system called power-ups that really pretty much would be its own complete talk. The short version is you can persist pretty much any behavior that you want into an Axiom store and then shut it down and then start it up again. Yes, really. Like, seriously, you can essentially completely persist your entire application if you really wanted to. And then even if your machine just like loses power, let's say that's an IRC bot, you turn the machine back on again, you run the machine again, and like the IRC bot that was answering trivia questions remembers what trivia question it's at. So that's pretty cool. And obviously, in terms of scaling down, I don't know how much better of a scaling down argument than I can give than it's just Twisted Web and SQL. Well, actually, Twisted Web is in the rest of my application, but it's just SQLite. You know, it's like the lowest common denominator. SQLite, there's probably like 100 or even 1,000 SQLite stores on each and every one of your smartphones. So if you have a nice beefy server, it can probably handle SQLite. So what sort of alternatives do you have? Because obviously not everyone has to use SQLite. Well, first of all, Redis. I think you could probably run Redis, use this with Redis. Running a single Redis instance on each and every one of your servers is not a completely unreasonable thing to do. The overhead for a single Redis instance is honestly not that bad. If you really wanted to, you could use Postgres. It's not a perfect fit, but you know, it still works. And the only thing that you really could not use is MySQL, because you should not use MySQL for anything ever. So longer-term storage. Well, why would I even want to talk about longer-term storage? Well, the first case is obviously money. If you compare, you know, the cost per byte of storing EBS, or storing something on EBS, so that's Amazon's sort of hard disks in the cloud thing, and you compare it to S3, which is their longer-term storage thing, and it's not even very, well, it's not even like tape backup or anything like that. It's still instantly available. But if you compare the costs, then you notice that S3 is basically so much cheaper. It's a huge difference. The other reason is durability. You know, it would be very nice, no matter what you think, eventually your server will go down. And even if you have like RAID 10 with God knows how many drives, then at some point your RAID controller will just be busted and it will start writing random junk onto the drives, and then you're still completely out of luck. So it would be nice if you have a more durable answer for backups. And finally, if you have multiple servers and you have long-term storage up there, then right now a user might be using server A, but then when the user is logged out, you put it into long-term storage. But when the user logs in again, turns out that server A is really, really busy. Server B needs it. Now either server B has to now find the problem of which on these thousands of machines in the cluster, where is the user store currently located, and then I'm going to ping that very busy machine and grab the store off of it and put it on my local machine, or it could just grab it from S3. In the case of, particularly in the case of Amazon, you can essentially consider S3 as sort of this permanently available data store all over around you. So those are the good reasons why you might want to do that. So what are your options? Well, I mentioned S3 and EBS a bunch of times because basically Amazon is by far the biggest provider of this service. They are not the only provider of the service, but you know they're essentially the most commonly used one. The biggest problem with S3 is that it doesn't support differentials. So essentially, what does that mean? You can't tell S3, okay, so I have a store here, and it's a gigabyte big, and these 10 bytes have changed, so can you please update these 10 bytes? You can't do that. You have to tell it, hey, here's the 10 gigabyte, or here's the 1 gigabyte entire thing again, please upload it. obviously, especially if you are in the case where you have where you have very large stores, we have like a gigabyte or more of data. If you don't want to be uploading that every single time. There's no obvious answer here for S3, I'm afraid, and the only people that I've found that have essentially solved this problem are Dropbox and Dropbox similar Dropbox alternatives, of which there are many. Now, unfortunately, most people will probably cringe a bit when you tell them that your server backend writes data to Dropbox. Mostly because things like, for example, Dropbox gives you absolutely zero guarantees about file locking. Basically, like Dropbox can just start writing into your file from underneath you. So I haven't really found a very good solution to this. Maybe if you're like on Btrfs or ZFS and you can use snapshots to like really guarantee that everyone stays off of this file or off of this directory from now on, then maybe you could do it. But this is mostly an open question for me. Right now, I just upload to S3 because my individual user stores are small enough that I just don't care. I'm using Twisted for this. It doesn't really matter. You can pretty much use anything you want, but there's two reasons why I want to mention that I'm using Twisted. First of all, Manhole. Who has used Manhole here? All right, a couple of people. What's Manhole do? Essentially, Manhole allows me to SSH into a running server and get a REPL inside that server, and I have some state inside that server be exposed to me. So in terms of like debugging and experimentation, this is amazing. Like you can actually go into a live server and change stuff, and it will also be reflected live into the behavior of that server. Obviously, that's not something you always want to do in production, but when you do need that, it is an amazing tool. Also for diagnostics and debugging. I mean, there's very little that can beat having an actual Python REPL. And like I said, anything will work. But the other reason why I think it's very important to mention this is because Twisted is an event-based system. So people who saw Simon's talk right before this, he mentioned this as well. The important thing is that, so Twisted is the thing on the left, and a traditional multi-threaded server would be the thing on the right. So while Twisted is concurrent, so it's doing the red task and the yellow task and the blue task and the green task concurrently, it's never doing more than one thing at the same time, whereas the one on the right is. So Twisted does not do more than one thing at the same time, most of the time. Why is this important? Well, Axiom blocks. So what that means is that while I'm doing anything with the Axiom store, so I am running a query, I'm inserting an item, I'm trying to get some items out of it, or any of that, that means that absolutely nothing else is happening inside my server. So no connections are being accepted, no bytes are being read or written unless they've already been handed to the kernel. The kernel can do whatever it wants behind my back, but essentially nothing else happens besides that single query. Now, the thing is that it turns out that Axiom is actually so fast that it simply does not matter. And that actually brings me straight to my performance argument. So the issue is that most benchmarks, well, they're pretty bad. There's a bull on this article, in this slide, and I have no idea why. So let's try and use some logic first to try and argue why this might or might not be a good idea. There's essentially two ways to getting better performance. Either you do less work or you do it faster. Because most of the time you can't choose to do, like simply scale down the problem size. So either you make it less work to do it or you do that faster. Here's a chart with some latencies. So this is a logarithmic chart, and essentially it measures how slow something is to get. So level 1 cache is essentially so fast that it doesn't even fit on the graph. Level 2 cache is a little bit slower, but it's still ridiculously fast. This is in nanoseconds. RAM, a little bit slower. SSDs are incredibly fast, as we all know. Local area network, assuming a really good data center. Then finally, hard disk, as in spinning Rust. And finally, going from a data center in Fremont, California, to AMSIX in Amsterdam. So the point I'm trying to make here is that local means that you have lower latency than pretty much anything that's not local. So if you're working locally, then virtually always you win on latency. Now, in most queries, with a traditional remote database setup, if you compare the query latency to the actual access latency, so how much time does it take to get the data in the right place versus how much time does it take to actually do some computation on said data, then it turns out that that query latency is almost virtually never the bottleneck. It can be, but it almost never is. Now, it's actually even better than that for the case for a fractal architecture, because it's not just a remote database versus a local database. It's a remote database versus a ton of very, very small local databases. So even if you have to do an expensive table scan, which most people, if they see it in the output of explain, they go like, oh well, this is a this is the hot path. This has to be fast. This has to be indexed. We can't accept a table scan here. But it turns out that if the number of rows is simply all of the rows for that single one user, a table scan on 100 rows is, in some cases, actually faster than doing an index lookup. So it turns out that, especially if you take into account how much time and effort you spend into even maintaining the index, then honestly, a table scan is fine. Now, of course, generalizations are always wrong, but computation is rarely the bottleneck. There was actually a presentation on Meerkat where computation was computation was not there, but I was expecting computation to be their bottleneck, but essentially, same thing happens again. I/O was the big problem. Getting data at the right in the right place at the right time is almost always your bottleneck. Now, if people really, 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 really want benchmarks, I wrote a package called Axiom Bench. You can pip install it, and it will do some stupid things like create a bunch of objects and then put them in the store and then take them out of the store again. Or there's a couple of benchmarks. The bottom line is Axiom is ridiculously fast, and if a remote database is fast enough for you, then assume that Axiom is about 2 orders of magnitude faster. So let me play advocate of the devil a little bit and try to poke some holes into my own design. Now, something that people have mentioned is that some data doesn't really appear to fit in. So what do I mean by that? Well, you have all of these nice user stores, and then you have these bits and pieces of data left and right that don't really belong to a user. For example, let's say that you're doing some statistical analysis, or you're doing some machine learning, or you have some very simple aggregate data. Now, it's users.aggregate, not user.aggregate. It doesn't belong to any individual user. Or for example, they have encyclopedic data. In my case, I work a lot with geospatial applications, so in my case that ends up being things like zip codes. I have a location and I want to go to a zip code, or I have a zip code and I want a name for that location, or whatever. The point is that it's world.data, not user.data. It doesn't belong to any particular user, so where do I put it? Well, there's no obvious place to put it. And this is very much a square peg round hole problem, given that I've just defined every store as being a property of a user, and now I have these things that are, by definition, not property of a user. So there's essentially 3 ways of dealing with that, and it's duplication, delegation, and separation. And so duplication is really simple. Essentially what you do is you take all of the data and you put it in every single one of the user stores, and then everything is local, and it's very simple. But of course the downside is you have to duplicate. First of all, size-wise, that can be a problem, especially if you're dealing with geospatial stuff. Very often you have these maps that are like gigabytes, if not terabytes in size. And it doesn't really make a lot of sense if one user wants to put a dot on a map somewhere, and that's like 1 kilobyte of data, maybe, and then you're like duplicating a terabyte of data in order to know where the dot actually is. So that doesn't really make a lot of sense. Then updates, of course, if you have 10 million users and it turns out that like a zip code changes, which does actually happen. People sometimes are surprised to find this out, but zip codes actually change on a regular basis. Usually they're small changes, but if you want your app to be correct, you're still going to have to update that data. And I'd much rather update one single source of truth than 10 million separated user stores. So basically, it's a good idea if you have limited data with very limited mutation. So secondly, you can delegate. So essentially what you do is you say, oh, well, this user, I find some way of determining that this data really does belong to this user. Now, the upside is, of course, no duplication, but the downside is that it's very, very complex, because this function of deciding, where do I even put the data, in many cases there's no obvious such case, and it's extremely difficult to come up with such a function that actually makes sense in the long run. The good news is that your queries are sometimes local. So this is a good choice if your usage is highly correlated with a particular user. For example, if you have sales data sharded by area, and you have a sales team for, Africa, then it makes sense to put the sales data for Africa in the sales team for Africa, even though sometimes maybe the Europeans will want to take a look at the African data. 99% of the time, the query is going to be local. So most queries will be local, and at least the aggregate queries will cross shards predictably. So you're dealing with something that will at least be predictably hard. And the other downside is very tight coupling, because let's say that you no longer have a sales team for all of Africa, but it turns out that South Africa is this massive market and it deserves its own sales team. Then suddenly you have a lot of data that you need to move, and it's not always obvious where to put it. And finally, it's by far the best method, really. It's separation. So basically, what you do is you simply turn these into their own stores, because nobody said that just because I have user stores down here, that doesn't mean that all of my application servers or all of my stores all have to be for users. It makes perfect sense for some store to be some other kind of data. So you end up with this group of user stores, and then you end up with this group of, I don't know, aggregate data or whatever. So another issue with this is that querying over all data is hard, or actually even much worse, querying across stores is hard. My answer to this is yes. Yes, it is. Now, there are two main reasons why people end up wanting to, assuming that your sharding vector makes sense, there are two main reasons why people want to do this: data analytics and transactions. So data analytics, for most data sets, separation. This is what I do. I use a machine learning library called scikit-learn, which I highly recommend. It's sometimes called scikit-learn, sometimes called scikit-learn. I'm not entirely sure what's up with that. But essentially, it's a machine learning library, and all of that data just gets put into its own store, and that works fine for me. Now, for big data, you generally already use specialized tools. You know, you set up a Hadoop cluster, and you're probably going to want something like HBase or Hive or something like that to actually store your data in. I think the Meerkat people were using HDF5. So they already have customized tools. So even a traditional database wouldn't be good enough. You want to get that data off into something where you can more efficiently query it. Is there a missing sweet spot where a more traditional database would have been fine as a Hadoop source and your individual small stores wouldn't? Maybe. I'm not convinced. What I am convinced of is that there's a lot of people who grab for the big tools, the big power tools like Hadoop, when honestly they could have done fine with a significantly more simple little piece of Python code somewhere. And the next reason is transactions. Now, cross-database transactions do actually exist. In SQLite, there's attached database, which sort of works as long as you disable write-ahead logging. It's at least carefully documented what the caveats for this are. If you use Postgres, then there's dblink, which, according to the FAQ, also sort of works. And finally, of course, and actually the Postgres FAQ for dblink sort of recommends this, is do it in your app, or do it in Python. Now, I realize that this is a fairly terrible answer, because really, the reason that we're using relational databases in the first place is so that we wouldn't have to do this stuff. And, well, we could just implement PyConZA again, but let's not. So who's heard of PyConZA? Okay, so PyConZA is an incredibly, well, I suppose it's not incredibly complicated if you compare it to its peers, but PyConZA is essentially an algorithm for a distributed cluster of computers to agree on something. That's it. It sounds kind of simple, but the problem is that if you look at it for too long, then your brain will start hurting. I've implemented PyConZA approximately 3 times, and that's 3 times too many. So I don't have a very, very good solution here. What I do right now myself is I sort of implement it in Python. So what I do is let's say that there's a transaction across 2 stores. Then I make sure that the transaction on the first store is at least reversible or not very destructive. So I don't throw data out. I just mark it as deleted. And then it pretty much works. It's not a great solution, but it's the best one that I can come up with so far. It's certainly the simplest. So what's some other issues that can occur with this kind of design? Well, there's no existing tools or frameworks. Sort of true. I hope that I've demonstrated with the use of things like SQLite and Axiom, which has been developed years ago, that there are tools. It might not just be very obvious. It's certainly not the most standard design using those tools. So it might not be obvious that you can use them to get to that kind of result, but they do exist, and it works fine. There are no frameworks. Well, that's true. I mean, you have Django, which if you want to build a web app, then Django will pretty much just light the way for you and figure out pretty much everything that you need to know. And if you have hosting services like Heroku that will completely take care of the hosting for you. And none of these things exist. For example, a fractal architecture on Heroku would be incredibly complicated because, for example, Heroku gives you very few guarantees that your dyno is going to keep running. I mean, it can die at any given time. And they really expect you to use a centralized database that takes care of persistence for you. So you're going to have to do a lot of things yourself that you honestly would expect as Python programmers to have been done for you. Now, I think it was Gandhi that taught us to be the change that you want to see. So I have tried to fix the situation a little bit myself. The first project that was publicly released that did this many years ago by the now unfortunately defunct DivMod was called Mantissa, and it also uses axioms. This is actually why Axiom was created in the first place. You can still get it, and it works fine, and there are people who swear by it. It is unfortunately somewhat arcane knowledge. It has a very, very low bus number, and it's quite hard to get into it because simply there's not a lot of people using it. So I have recently started to try and fix this thing myself. So obviously my thing is called Exponent because it's the thing that comes after the Mantissa. And there's a thing called Maxims, which is essentially reusable, persistible items for Axiom. So for example, if you think about your current ORM, and let's say you want to log, you have a current item, you already have a defined item, and you want to log when that item is created, when new instances of that item are created. How hard is it to do that in your current thing without touching your schema? With touching your schema, it's usually not very hard. Okay, but then let's do it for 20 classes instead of one class. Oh, well, okay, then you can sort of do it sometimes with multiple inheritance. Łukasz Langa has a good talk about this that he already gave at PyConPL, probably going to be coming up at the next PyCon US, on all sorts of nasty things that happen with multiple inheritance in Django ORMs. And basically, this is much more complicated than it seems. In Maxim, it's a single decorator to your class, and it will basically just work. And this is essentially only made possible through the magic of Axiom. And I think that is the end of my slides. So I will leave it up to you to ask me more pointed questions about what is wrong with this. It's your turn to be advocate of the devil, and thank you for your time.
Thank you.
So right now, it's essentially one process, which is that has a root store where all of the things like configuration and pretty much everything that's common to everything is stored, and then user stores talk to that. So and then that single process. So it's all one process per machine. And that speaks HTTP and WebSockets and AMP over TCP. So and that works fine because the individual. So like I said, it's twisted. So it has to deal with the blocking API. But it turns out that all of the requests that I've managed to, all of the queries that I've managed to throw at Axiom are so fast that it really doesn't matter at all. So. So, yes, but there's a couple of obvious solutions to that. For example, what you could do is you could keep the shard locally. The obvious issue there then is what do you do when so essentially you're creating a local cache, and then you have the issue of cache invalidation, which there's 3 hard problems in computer science. There's 4 hard problems in computer science. There's naming things, cache invalidation, and off-by-1 errors. Yes, it is quite hard to get it back. Hopefully, whatever thing that supersedes S3 in my design that takes differential updates will also serve me differential updates. So essentially, what I'm looking for is hosted S3. Is hosted rsync, because that would pretty much solve that problem, I think. Essentially, the idea right now is that if S3 fails, then that's the backup. So if you want more reliable, data storage on top of that, of course you could implement that yourself with all the usual caveats of indeed, your data simply being stale. But if you're working locally and the machine crashes, then essentially the data back guarantee that you get is about as good as SQLite's, which is pretty much as good as it gets. So Axiom pretty much executes SQLite queries instantly, or at least synchronously. So when it returns, you get exactly the same guarantee that SQLite has that the data actually made it to disk, which is fairly strong. So if the hard drive in the machine completely dies, or the RAID controller just starts writing random crap to the disks, then then you have data loss. But then again, you would pretty much have data loss in any other. I mean, at the end of the day, once you're talking about hard drives physically failing or RAID controllers physically failing, then you're pretty much always out of luck. So I think it's still fairly good. It might actually be slightly better than what you have with a centralized database because at least your outages will be local, as opposed to MySQL went away and the entire database is basically just gone. So does that answer your question? No. All right. So the question is, which server does a user end up getting serviced by, right? Okay. So yes, the answer in that case would be mostly whichever server they end up talking to. That server's responsibility is then get that user's data and service whatever request they want. You could try more complicated ways of handling that, which would have advantages for obviously data locality, so that that server still has the current version of the store locally, and then the user can tap into that. But it's A, more complicated, and B, the current solution is simply so fast that I have not had a need yet to implement that. But there have been several suggestions for moving that forward, and the day that I need it, I will probably end up writing it, and it will probably end up getting open source. So, but right now, haven't had the need.
One more.
Right now. So the way we use S6 is that we that essentially whenever the user logs out, then the current state is pushed to S3. That has the unfortunate. So right now that's okay because uploading things to S3 is fairly fast, and users try not to, or at least users don't generally log in immediately. And when they do, then okay, well, we're writing this old version back. There's still a race condition there, but I know there's a race condition there, and I know I haven't fixed it yet. But fortunately, the race condition is probably fairly benign because as soon as the user then logs out again, then I will be uploading the new versions of the store, and the local version is always consistent, even if the remote S3 version isn't. And at least within a file, it will always be consistent. So the only way that it could ever be inconsistent is, for example, if let's say that you're storing images in the Axiom file storage thing, you're storing images, and you're already uploading an image that has no reference in the store that is uploaded to S3. So you might get inconsistent data there, but at least it will always be eventually consistent. And suddenly I've realized that by doing this, I've reinvented NoSQL. So yeah, it's an eventually consistent data store. Mm-hmm. Right. So so essentially the question is, what do you do when a user, well, actually you just open two tabs and the user opens two tabs and they both connect to the service, or the user has an iPad that connects to the service and they're running machine. So how do you fix that? Well, the obvious way of fixing that is make sure that that there is always at any given point only one single machine trying to service a given user. For a very long time, and actually that means up until today, I have not yet had to deal with this issue because it turns out that you can service a really, 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 really large amount of requests off of a single machine, as long as that single machine is fairly fast. But of course, as soon as you deal with multiple machines, then that doesn't work anymore. So the obvious solution there would be simply make sure that all machines for a given user always get handled by the same machine. So the easiest implementation for that in Exponent would be probably take requests from anywhere, but as soon as they log in, see if there's any other server that's servicing those requests, and then basically just proxy. Because the issue is you can't reliably tell users which machine to log into, because there are malicious ones that will simply log onto as many machines as possible just to try and get you to do as much work as possible. So yes, there will need to be a proxying thing at some point. And it was sort of, like there's a dummy implementation in Mantissa, but I don't think it's actually literally distributed. So I don't think that's written yet, but it will be.
Thank you